Howdy, class. So today we are talking about something called enthalpy, but first we're going to start by talking about something that we've discussed a little bit already, and that's work. So determining the value and the sign of the work related to a system depends on the reaction or process conditions. Sometimes we're not talking about a reaction, we're talking about a physical change like melting an ice cube. So still depends on the conditions where this reaction and process are happening. So we want to learn more about work, this work thing. Um, so there's two scenarios. There's two types of conditions that you could have your reaction occurring in. Basically, these are the only two conditions that we're worried about, is constant volume conditions or constant pressure conditions. So constant volume conditions, if we have constant volume conditions and we are performing an explosive reaction, like the one that your book describes, which is sodium azide. It's found in your airbags if you are ever in an accident. Hopefully you aren't. But if you ever are, when your airbag deploys, there's sodium azide in there. Another explosive reaction we can talk about is that hydrogen gas and oxygen gas reacting to form water. That combination reaction, it's pretty explosive. We've seen with hydrogen balloons, that demo I've shown you before. So any explosive reaction, if we are carrying this out under constant volume, that means we have a closed container and we are not letting that container expand in any way. So it's like a steel drum or something. And it's closed, it's sealed, so this explosive reaction is happening in this closed sealed container. And when that happens, that will cause a drastic increase in pressure in the closed container. So think about shaking, think about when you shake a soda bottle. So if you shake up a soda bottle, it builds up a lot of pressure from the gases inside of the soda bottle. And when you try to open it, the cap will pop off, maybe when you're popping champagne bottles, or the cap, or if the cap doesn't pop off, you'll still get like lots of foaming. Your soda will try to, expand now that it doesn't have a seal. It will start to expand because there's increased pressure, so it will, your reaction or the gases involved will want to expand and get out of the way to lower the pressure. So remember from experiment 5, when we increase our volume, we decrease our pressure. So when you open your bottle that you shook, you are allowing the volume to increase because you are, letting the gases escape into the rest of the room, the atmosphere. So the gases now have a much larger volume that they can take up, which decreases the pressure. So that's what happens there. But in our constant volume container, this explosive reaction would cause a really big increase in pressure. And that's not usually ideal. So we'll talk a little bit more about that, but we need to look at these two scenarios to understand work a little bit better. So under constant pressure conditions, we have our container which is allowed to expand when an explosive reaction occurs. So that means that we have our container with this like movable piston. That's my great drawing of a piston. So if an explosive reaction happens, that's my drawing of an explosive reaction, and the pressure starts to increase inside of our container, it's going to push this piston up to allow the volume of our container to increase so that, well, I guess our container usually has like, I don't know, extra room like that. But to allow our container to expand so that the pressure can decrease and stay constant. So that's how we maintain constant pressure conditions, is that we allow the volume to change. When we have constant volume conditions, the pressure changes. So constant volume means there's a change in pressure. Constant pressure means there's a change in volume. So when we have constant pressure conditions, our container is allowed to expand, keeping the pressure the same. So think about that pressure volume relationship you discovered in experiment 5. So if there's a big explosive reaction happening in this container, that's going to increase the pressure, but we want the pressure to stay the same. So we have to increase the volume so that when we increase the volume, the pressure goes down. So we want to increase our volume so that the pressure can go back down to what it was before, so that we can have constant pressure. So this is how we define work, actually, is work is equal to negative P delta V. So P is the external pressure, so the pressure pushing in on the system. I'm going to erase my drawings because they're not very good, and try to redraw this. I have a better example on the next slide, I think, but there's a really good picture in your textbook. So we have this here container, and we have our piston here. So external pressure, that's the pressure pushing in on the system. So causing this piston to be lowered and decrease the volume. So P is external pressure. You want to remember that sign, that convention, which direction the pressure is coming from. Pushing on the system, not the system pushing out. So we're pushing on the system, our external pressure. And delta V is the change in volume as a result of the motion of the piston. So if we've got, a lot of external pressure pushing our system in, the opposite of our explosive reaction. So say this is a reaction that absorbs energy. It's going to kind of suck suck the piston in and lower the volume of our container. So say that's what happens. Now I'm going to draw my piston like this. So now our volume is smaller because our pressure was pushing that in. So this change in volume is our delta V as a result of moving the piston because of the external pressure. So work is equal to negative P delta V. So now we can understand work a little bit better in order to understand changes in energy a little bit better. Alrighty, so under constant volume conditions, no PV work can be done because delta V equals 0. So PV work, I want to distinguish between other kinds of work. So there's also electrical work that could be done. We're not going to discuss that in this course. So we're only going to talk about PV work. So you can just think of the definition of work as only this PV work. That's the only type you need to worry about. So delta V equals 0 under constant volume. So constant volume means there's no change in volume. So delta V equals 0. So if we plug that in to our work equals negative P delta V equation, we find that work equals 0. So there's no PV work being done. And then if we plug it into our delta U equation, so delta U is equal to Q plus W, our heat plus work. And we plug in this negative P delta V for our value of work, but this delta V is 0. So this whole thing cancels out, and we find out that delta U is equal to heat under constant volume. So under constant volume conditions, the heat of the system, or the heat related to the system, is all that is involved in the energy change. There's nothing else involved in the energy change but the heat flow. That is it when we have constant volume. So that's what this little V represents, constant volume. Heat is equal to the change in internal energy. However, like I said, most reactions occur under constant pressure conditions. We don't usually go around sealing things up in really tight steel drums so that we can contain our reactions, mostly because it's not really safe. If we're doing some explosive reactions in these containers, that pressure builds up, and unless we have a really good seal, it could get dangerous if the pressure builds up and something like the lid pops off. So instead, we perform most reactions under constant pressure conditions where we have an open system. Our reaction is open to the atmosphere so that pressure remains constant. So sometimes instead of using a piston, we just leave the system open. If the system is open, then whatever gases we have, typically we're talking about gases in these reactions, whatever gases we have can expand throughout the entire room, and we keep the pressure of the rest of the room. We keep the atmospheric pressure in our system. So most reactions occur under constant pressure conditions, and constant pressure conditions mean that there is PV work done by the system. So constant pressure means that volume does change. So a change in volume is not equal to 0. And this isn't delta P, it's just P. So our constant pressure is still going to be a non-zero pressure because that's just how the world works, unless we're out in like the middle of space maybe, where there's no pressure. But I don't think that even works out in the middle of space. I'm pretty sure the universe, has a lot of pressure out in space. But regardless, everywhere in the universe that we care about, there is pressure that is non-zero. So this term is not going to equal 0, and there will be PV work done by or on the system. And now we're going to talk about a new term called enthalpy. Enthalpy we call, or is denoted with this capital H. It's probably related to Greek or something, but enthalpy, capital H, is a thermodynamic property that describes heat exchange under constant pressure conditions. So, like I said, heat exchange, or Q, under constant pressure, this QP, is enthalpy, as I'll show you down here in the next equation. So enthalpy is the sum of the internal energy of the system plus pressure times volume. So we could write that as, and I think I will on the next couple slides actually, write that as H equals U plus PV. Sometimes we use an E instead of a U, so I might use that sometimes interchangeably, sorry. So this is our definition of enthalpy, and this is our definition of the change in enthalpy. So the change in enthalpy, we just put little, deltas everywhere. So delta H is equal to delta U plus P delta V. So you might wonder why there isn't a, delta here, but that's because we're at constant pressure, so there is no change. So we only need to worry about the change in volume. So we write this, and this looks really familiar because I had it right up here. Delta H is equal to delta U plus P delta V, which is equal to Q, or heat, under constant pressure. So enthalpy is equal to the heat exchange under constant pressure, as I said here in the definition of enthalpy. So your heat of your process or your reaction or whatever is the same as your enthalpy of that reaction or process or whatever. So let's look at work a little bit here. I'll do a practice problem for you. So against what external pressure must a gas sample expand from 50.0 milliliters to 219 milliliters to do 8.34 joules of work? So let's draw our system. Sometimes it helps to draw pictures. So we are going from, I'm going to draw my little system here. This is my piston. It's really bad. So this is 50 milliliters, 50.0 if we want to pay attention to our sig figs, which is always good. And we are going to expand to 200 milliliters, 219 to be exact. So we want to expand and we want to be doing 8.34 joules of work. So remember, work is equal to negative P delta V, and we want to solve for pressure. So I'm going to solve this for pressure. Divide by negative delta V. That gets rid of that and that. Negative delta V. So P is going to be equal to negative W over delta V. All right, so we have W. W is 8.34 joules of work. And let's see, what do we have for delta V? So our delta V is going from 50.0 milliliters to 219 milliliters. So this is V final, and this is V initial. So delta V is going to be V final minus V initial. So if we calculate that real quick, that will be 169. I think I did that correct. Milliliters. So 169 milliliters is our delta V. So now we can plug all of this in and calculate. So remember, we want to consider our sign conventions here. So our work, so if you remember back to the last time I lectured, when we were first introduced to work, when the system is doing work on the surroundings, work is negative. When the surroundings are doing work on the system, work is positive. So if we have an expansion, so our volume of our gas is increasing, that means that we must be doing work on the surroundings because our system is in here. So we are doing work on the surroundings, which is causing our container to expand. So when we're doing work on the surroundings, work is negative. So work should be, in this case, negative 8.34 joules. And that is good because pressure has to be positive. So if we plug that stuff in, we've got negative and a negative, which is going to cancel out. So 8.34 joules over 169 milliliters. But we want to make sure all of our units are going to cancel out. So I'm going to erase my picture now so I have more room to work. So now, let's see. This 169 milliliters, that's cool, but our little hint here about our unit conversion tells us that 1 liter atmosphere is equal to 103 or 101.3 joules. So our energy is in joules, or our work, which is a type of energy, is in joules. So we want, so if we have this in joules and we want to get our volume into liters, then that will give us a pressure in atmospheres. Cool. So I'm going to do that. I'm going to convert 169 milliliters to liters. There's 1,000 milliliters in a liter. So this is 0.169 liters. And I'm going to convert my joules right now too. So we have our work in joules. So 8.34 joules times, so I'm going to use this as a unit conversion, a conversion factor. Remember back to our dimensional analysis that we've used so many times throughout this semester. Oops, I don't know why I want that to be kilojoules. I don't. It's joules in this conversion factor. So 101.3 joules. And on top is going to go this liters atmospheres then. Okay, so let's calculate my work in liter atmospheres instead of joules so that we can finish our calculation. So 8.34 divided by 101.3 is 0.0823 liter atmospheres. Okay, so now we have, this is my work, so remember this is still work, and this is delta V. So we plug it all in, and we find that P is equal to 0.08233 liters times atmospheres divided by 0.169 liters. That's how we get our liters to cancel out. And our answer is going to be, I'm going to erase so I can write it. Our answer is going to be 0.487 atmospheres. There we go. So we need to have 0.487 atmospheres pushing on our gas sample for the gas sample to expand from 50 milliliters to 219 milliliters. So it's going to increase in volume and end up doing 8.34 joules of work. Cool. All right. So I'm going to break here and start the next set of videos going into enthalpy in some more detail.